So what I've drawn here is a little teeter-totter to try and introduce the idea of something called moments. Now, if, dad or mom is holding the teeter-totter, you can keep things level, but as soon as they let go, this is going to turn down this way. And I think a lot of us intuitively have a notion as to why, and that is this kid's heavier. And that's going to put more turning force. Now, what we're going to use is something called the moment. So the right moment is the tendency for this system to want to turn in accordance with that force. So that's simply going to be the distance to the center point times the mass. So it's going to be 30 times 2. It's going to give you 60. And if you were to keep track of the units, you have meters times kilograms. So I'll just call that kilogram meters, kgm. Yeah, let's make that look like an M. There we go, thank you. On the left-hand side, anyone want to guess what the left moment would be?
40.
Yeah, 40. Good, thank you. So it's going to be 20 times 2, which is going to be 40, again, kilogram meters. Now, if you wanted to keep things kind of more equal and maintain that equilibrium spot, then what you could do is you could slide this kid a little bit closer. So what if we slide him to a point, say 4/3 of a meter away from our center point or our fulcrum? Then let's check out the new right moment. And that new right moment would be 30 kilograms times 4/3 meters. And guess what? That's going to equal exactly 40. Okay, so we got something that's nicely in balance now. Yay. So the big kid just has to scoot up a little bit. All right, so in general, this idea of the moment is the moment about a point is a tendency to want to rotate around that point. So the moment about a point is the tendency of a system to want to rotate around that point. Okay. Give you a second to catch up on that. All right. Let's click over to an example like this. So we've got 3 points in this example, and they want us to calculate the moment around the y-axis and the moment around the x-axis. So each of these points has a mass which is labeled. So this point in the first quadrant has a mass of 8, and the second quadrant has a mass of 4, and the second quadrant has a mass of 2, and the fourth quadrant has a mass of 4. So these are the masses of these weights, and we want to see what kind of force that exerts on things. So we want to calculate the moments. Now we'll start out with the moment in the y direction. So we'll call it m sub y, which is what they have here. Let's highlight that over here. There's our m sub y. Now the m sub y is going to be the tendency for this to want to rotate around the y-axis. So, okay. Now if we're rotating around the y-axis, then this force of 8 here, or the mass of 8, is going to be felt at a distance of 3 away from the y-axis, or away from x equals 0. So as far as calculating our mass is concerned, excuse me, the moment is concerned, the contribution from this point right here is going to be this point, or this total right here, 8 times 3. And then we're going to do likewise over here. So this point has a mass of 2. Its distance away from the center is going to be 1, but it's to the left of center. So it's going to be -1 times that 2. That's going to be its tendency to want to rotate around the y-axis. So that's going to be this one right here. And finally, we have one last point, which is our 4 in the 4th quadrant. It's a distance of 2 away from the y-axis. So its tendency, it wants to rotate things around with a force proportional to 4 times that distance of 2. So that's where all those things come from. If you multiply this all up and add it, you're going to get a total of 30. And that's m sub y. That's the moment. That's the tendency to want to rotate around the y-axis. Now, eventually, we're going to use that to try and find the center of mass. That would be like the balancing point that you could put your finger underneath to hold everything. But let me repeat that calculation for m sub x. So this time we're trying to rotate around the x-axis. So let's start here with this mass at 4. It's going to want to push down on, say, like a hinge rotating around the x-axis with a force of 4 multiplied by its distance away from the x-axis. Well, it's 1 below the x-axis. So you're going to have 4 times -1. That's going to be its contribution to the moment. What about this point up here at 8? Or, yeah, the point at 8. It's going to want to rotate around the y, or the x-axis. It's going to push down with a force of 8 multiplied by its distance away from the x-axis, which is our y-coordinate of 2. So you're going to have 8 times 2. And the last one, I hope you can kind of see where this one's going to come from. We're going to have a force of 2 pushing around the x-axis multiplied by a distance of 1 above the x-axis, and that's its contribution to the moment. So you get these two contributions. Well, these 3 contributions give you the moment around the x-axis, which is 14. But these 2 numbers are important, m sub y and m sub x. We can use those to calculate the actual center. And the formula for calculating the center is given right down here. Right here. So if you take the sum of all these things, sum of the masses, total up the mass, and then divide each of the moments about that mass, then you get the center of mass. The center of mass also goes by another word, sometimes called the centroid, but it'd be the balancing point. It'd be as if you had a plate with these weights on it and nothing else. Where would you put your finger underneath to hold it up, to keep it in balance? And that point would have these coordinates, 15/7 for the x-coordinate and 1 for the y-coordinate. There's something strange that kind of always bothered me, and I understand why it's there, but doesn't make me feel a lot better. And that is, to find the center of mass in the x direction, you're going to take m sub y and divide it by x, divided by m, divided by the total mass of your object. In our case, the total mass was 14. That's right up above here. But conversely, to find the y coordinate of the center of mass, you take m sub x and divide it by m. So you got to play a little switcheroo game here at the end. Try and find that center of mass, but there it is. One thing that you should do when you're all done is look at it and see, well, does that make sense? Is that where I would think this should be? And yeah, I guess it's not too bad. Keep in mind that 8 is the big kid on the block. It's the heaviest of these three objects, so it's going to tend to pull the balancing point towards 8, whereas 2 and 4 are a little bit lighter, so kind of out of luck on that one. All right, that's about it for this example. How are we doing on that one? Hopefully it's just a little bit of arithmetic and introducing some new terms there, or moments, and centroid, which is just your center of mass. Okay. I did send you guys a handout the other day, so, or actually earlier. So let's take a look at it. And for that, I'm going to switch over to here. And let's see if we can't find the center of mass for an object like this. So center of mass for an object like this, well, we're going to have to do a few things here. Now, first of all, I'm going to put coordinates of 0 and 0 right down here. And then these tick marks are going to be units of 1. So 1, 2, 3, and 4. 1, 2, and 3. Okay, looks good. And let's work on finding the center of mass in a couple different ways. Now, to find the center of mass for this kind of a configuration, one thing that's going to be helpful is if we know what the center of each of these little plates are. Now, I've kind of divided this up into 3 plates, and you can do this different ways. You can do it this way. I did it vertically. It's up to you. But if I want to find the center of mass, I first got to start by finding the coordinates of the center of each of these little regions. So let's start by finding the coordinates of the center here for a sub 1. So for a sub 1, well, looks like it's going to be here and here. It looks like it's going to be at the point 1/2 and 3/2. Okay. How about the coordinate of the center for a sub 2? What's that one going to be? Someone? All right. I need some love out there. Come on. Help me out.
2 1/2.
Thank you. 2 1/2. Just get a little nervous that sometimes my connection didn't break or something like that. So thank you so much. Okay. And then for a sub 3, it'd be 3 1/2. We'll call it 7/2 and 1. So those are the coordinates of our centers. And we're just taking the center to be the geometric center of each of these. This, by the way, is regarded as what's called a planar lamina. Basically what that means, it's a uniformly thin and dense sheet. So that's going to make our calculations a little bit easier in terms of finding the center of mass. Well, let's see about finding x bar and y bar. Now, x bar is going to be the tendency to rotate. Well, let's see. It's going to be m sub y divided by m. M is going to be the total mass of each of these objects, or of all of these objects. So let's take a look at the total mass here. The total mass is going to be represented by the area. I'm going to assume that it has some kind of a density of 1 so that the area and the mass are going to be the same. Width times height is going to be 3 plus 2 plus 2. So our mass, M, is going to be a 7. I need to do 2 calculations. So the first one is to take and figure out M sub y. That's going to be the tendency to want to rotate around the y-axis. So for instance, we're going to take this mass, the mass for a sub 1, which is 3, and multiply it by the distance away from the y-axis that this point is. And that point is 1/2 to the right of the y-axis. So 1/2 times 3, that's its contribution to the moment around the y-axis. Likewise, if the y-axis was some kind of a hinge, this would want to swing around that hinge or press down with a force equal to 2, which is the area, times 2, which is the distance away from the y-axis. And last but not least, this plate has a force of 2, and it's acting at a distance of 3.5 or 7.5. So 7/2 times 2, that's its contribution to the force or the moment around the y-axis. That is, its desire to turn this system around the y-axis. So if we multiply all those together, that's going to be 7 plus 4 is 11, plus 1.5, it's going to be 12.5 divided by 7. Or you could also think of that as 25 over 14. Okay, so let's see, 25 over 14, that's going to be a little bit less than 2, not by much. We'll calculate that in a minute. Let's work on M sub x. The tendency for this to want to rotate around the x-axis. And dividing M sub x by M was 7, is going to help us calculate the moment in the y direction. So let's repeat this kind of a calculation that we did up here, down here. This time we're trying to rotate around the x-axis. So I'll start with the mass of this plate, which was 3, times the distance that this is away from the x-axis, which is 3/2 or 1.5. And then we want to do likewise here. The mass of that plate is 2, and it's going to push down with a force of 2 at a distance of 1/2. And finally, this plate pushes down with a force of 2 equal to its area times a distance of 1. So if I multiply that out, that's 9/2 plus 2/2 is 11/2. Call that 2 or 4/2. 11/2 plus 4/2 is 15/2 divided by 7 gives you y bar, the y coordinate of your centroid.
May you just repeat how you found the distance for the A1 center of y 3/2?
Sure. I just took the geometric center here, and the geometric center, top minus bottom, is a distance of 3, so halfway between there is 1.5 or 3/2. that help out, Marissa? So right here, the top edge is at height of 1, bottom edge is at height of 0. So the geometric center of that would be at 1/2. And from right to left, well, the center of this would be 1 plus 3 divided by 2 gives me 2. So you're just looking at the geometric center of those. Now there is something peculiar about this center point. 25 divided by 14 is about 1.7857, so we'll call it about 1.79. 15 divided by 14 is about 1.07. So we'll call it about 1.8 is about here, and 1.07 is going to be a little bit north of that. So somewhere up here. Does anyone notice anything peculiar about where that center is?
It's not on the plane.
Yeah, it's not on our little weird shaped plate. So basically you can't balance it at just one point because the center of mass is actually off of this plate. Now that's okay, it's not something we have to worry about. Our goal is to try and find that center of mass. So, and we did. So that's where we can stop and say, all right, the rest of the problem is for you engineers. So when some of you, I know there's some engineers out there, when you guys get on to graduate school and stuff like that and figure out how to deal with this problem, send me an email. The math part, though, is done, so we're good there. Okay. Well, let's keep going then. There's no comments or questions on this. And what's going to happen is that we're going to have to start turning our attention to functions that are not nice, even sheets, that are a little bit irregular. But we're still going to want to do this calculation. We're still going to want to find the center of mass. So for instance, up above, our calculation that we used, we divided by, was m. That represented the total mass of the system. When we start working with curves to find that total mass, since we're assuming that it has some kind of a uniform density, it's just going to be that density times the area. Okay, that's fine. And the area is just going to be the top function minus the bottom function. That's going to be your m. That's going to be the bottom number in our mass calculation, or our center of mass calculation. It's going to be right here. But we're going to need 2 more numbers. The moment about the x-axis. That's going to be a little plate's desire to spin this around the x-axis. We're going to work this much like we did our previous problem. And that is, we're going to find the center of that plate and find that center's distance away from the x-axis. That's where the pressure is going to be felt on that plate, is this desire to rotate around the x-axis. Now that distance, I think it might have been Marissa's question, and it was a good one. That height is what's in the middle of these two things. And it seems to me I might have been doing something by subtraction up above for A1, but in all honesty, what we should be doing to find that middle part is averaging. So the y height here is going to be the average of these 2 points right there. So this is going to be, let's see, should write it with them. function notation I have. So it should be f of x plus g of x divided by 2. That's going to be the center of this one little plate or slice. So the midpoint is going to be right there. F of x plus g of x divided by 2. Okay, so that's where the force is felt. But how much force do we have? Well, the force you have is really a constant, which is the density times the area of that plate. So what's the area of that plate? Good question. The area of that plate is simply going to be the distance of that plate, the height, times the width. So the height times the width, height is going to be f of x minus g of x, and the width is going to be your dx term, as always. So this idea of a slice that I've used in chapters 6 and 7 is coming back again here. We're going to use that slice. But this is the formula for the moment around the x-axis. And we can, and maybe we'll clean this up a little bit. You can take the 2 out there if you'd like. That's fine. But I'm just going to leave it there for the moment. I want to work on finding a moment around the y-axis. That is, this tendency for this function or this plate to want to push its way around the y-axis, as if this is a door hinge and you're pushing down. How much force do we feel from this one plate? Well, it's going to be a couple things. It's going to be the distance away from the y-axis that your plate is times the area of that plate. So let's work on each one of those. Now the distance away from the y-axis is just going to be x. And x is going to vary between A and B for your particular planar lamina. In the y direction, it's going to be the area of that one slice is going to be the height times the thickness. And the height is just going to be exactly what it was up here. F of x minus g of x times dx. So that's what you're going to set up for this particular, or for any particular centroid, center of mass. So that's where we're headed, is working with these things. So that's the general setup. I want to do some particular problems, but if there's something about here, something in the notation that maybe you're a little unsure of, let me know. You can handle it now. And I hope to do a lot of examples before we move forward from this section. Okay. So let's start with this example. 7x plus 8y equals 56. And x equals 0 and y equals 0. We want to find the center of mass for this thing. So that'd be the tendency to want to rotate around the x-axis. Now, I'll help you out and I'll ask you a question at the same time. Your graph It's going to look kind of like one of these. So there we go. There's our graph. So while you copy that, think about where the center of mass might be. What would you expect for the center of mass? Which one of these? And we don't have to answer it correctly just yet. We can go back and look at that later. Let's see if we can't think about it a little bit. Well, I think this one is too close to the bottom left that I don't like that possibility. Same with this one. So I'm thinking it's either this one or this one. Kind of hard to tell. It is a little bit more bottom heavy. So
The 7 and the 8 are switched.
What's that?
The 7 and the 8 are switched. They don't solve anything. So X and Y.
7 and 8.
Like the highest is 7 and
Oh,
1.
no, okay, yeah. Yeah, I didn't see that about the graphs. Okay, yeah, there's a couple. Oh, all right, so we can eliminate one that way. Hopefully you remember how to find some X and Y coordinates. If we set Y equals 0, you're gonna get the X-intercept would be 8. So that'd be out here. So I guess we can eliminate this one. This one can't be it. So I'm going this one. That one looks pretty good. So somewhere a little bit north of, a little bit to the right of 2.5, and I don't know, not quite 2.5. We'll see. Yeah, well, good observation. I didn't even notice that. Thank you.
Yeah.
All right. So let's go back here and draw ourselves a little graph. There. So we got a little dx slice here. And let's label some points here. This would be 8 and 0. And this would be 0 and 7. Right there. And if you solve this equation for y, you'd end up with y equals 56 minus 7x divided by 8. Okay. Well, the first job that we need, we're going to need a total of 3 things. We're going to need m sub x, and m sub y. M is just going to be the area of this region. Now, there's a couple ways you can calculate the area of this region. What would be the calculus approach to calculating the area of this region? How can I find the area of all this?
The top minus bottom.
Top minus bottom. And then what?
Integrate that.
Yeah, awesome.
From
Thank
0
you.
to
Perfect. 0 to what?
8.
8. Nice. All right. So top minus bottom, 0 minus 8, or 0 to 8. And since the bottom is just y equals 0, let me just put 56 minus 7x over 8 dx. Now, in getting ready for this lecture, you can bet that I took the easy way out. I didn't integrate this. Not that it's hard, but what's the easy way to find this area? No one? Y'all gonna work
Base
hard?
times height.
Yeah, 1/2 base times height. 1/2 8 times 7. Hey, that's 28. Yeah, you don't get bonus points for working hard. But working thoughtful can help you out. So cool, thank you. So that's our m. Want that. Let's work on m sub x next. This is the tendency for this to want to push around the x-axis. So that's tendency is going to be felt right here at the center of that plate. So let's see. We're going to integrate between 0 and 8 because these slices can come from anywhere from 0 up to 8. And we want the distance, or excuse me, the point of that midpoint, where that force is going to be felt, we want the coordinates of that. And that's just going to be 1/2 of the average of the top function and the bottom function. So if I add these two together, then that's going to be, or add them together and divide by 2. Well, fortunately, the bottom is 0. So it's really 1/2 of this plus 0. 56 minus 7x divided by 8. I'll put in a plus 0 there just to help keep you oriented. But what this is, it's the height of that midpoint on this plate. And then I need the area of this plate. The area of that plate is going to be the height times thickness. I've got you back on the thickness. That's just dx. What about the height? How tall is this?
(56 minus 7x over 8).
Yeah, 56 minus 7x over 8. Beautiful. Now, in terms of finishing this up, you've got an 8 and 8. 64 times 2 is 128. So it's going to be 1 over 128 times the integral from 0 to 8 of, since we've factored out the denominators, it's just 56 minus 7x squared. Yay. And I'll let you play around with that on your leisure, which you'll end up with 196 over 3. Okay. How are we looking with this first one?
Mr. Parent,
Yeah, please.
can you go back, not go back, but can you just say what the two terms in parentheses mean? Like the 56 7x.
Sure. So this is the height of the midpoint. So it's just the average of the top function and the bottom function. Unfortunately for us, the bottom function was 0. So top plus bottom divided by 2, really. So maybe I should have written this a little bit farther over, but all of this, half of the top function plus the bottom function, that's that midpoint, because that's where the pressure to turn around the x-axis is going to be felt. Since this all has the same density, we're going to think of that pressure as being felt right at that point. And then this part of it is the actual area. That's the force of the plate, is the area. It's really the area times the density. Density is rho, but that's going to cancel out. So I'm not really even going to write that. Maybe I'll write it in this one. What's the area of one plate? Is that what you're looking for? Does that help out?
Yeah, it was. Thank you.
Sure. Thank you. Good question. Let's do the same thing for m sub y. This is going to be the desire to turn around the x-axis. Or excuse me, to turn around the y-axis. So we'll start with this distance here. Now the thing about this dx, what I've drawn is really a gross over exaggeration of dx. Dx is an infinitely thin slice. and its distance, you don't have to do any averaging kind of thing. Its distance is just x. So we'll keep that in mind as we calculate m sub y. So again, it's going to be an integral from 0 to 8. This time it's going to be the area of this, which we just calculated. So it's going to be 56 minus 7x over 8 times dx. So again, it's the area of one plate. Times its distance to the y-axis. Isn't that special? It's just x. So distance to the y-axis.
Hey, Professor,
Yes.
wouldn't the integral be from 0 to 7?
No. Good question. But our slice is still a vertical dx slice, and those slices can be taken anywhere from 0 to 8 along the x-axis. If we were taking a dy slice, then yeah, we'd probably be integrating from 0 to 7.
Okay, thank you.
No, thank you. I'm sure that somebody else had that same question in mind. All right. So, you know, again, you can clean this one up. This is 1 over 8 times the integral from 0 to 8 of 56x minus 7x squared dx. And fast forwarding as before, that's 224 over 3. Now, if you account for the density, which is rho, then that's going to put a rho here times rho and a rho here. But let me show you why I don't really fuss with the density. Because the last thing you have to do is you have to calculate the coordinates of the center. So last thing to do is we want x bar and y bar, which is m sub y over m and m sub x over m. I got to confess that when I was a student, this used to drive me mad. I was just so bothered by that. But it is what it is. We've already got the numbers. Let's just plug them in. So m sub y is 224 rho over 3 divided by 28. I should probably put in a rho here as well, because that would be the mass if I was putting in the rho. So divided by 28 rho. And then m sub x, which is 196 rho divided by 3 over 28 rho again. And here's where we see that that term of rho really doesn't matter. It's going to cancel. So whatever the density was, as long as it's a uniform density throughout the plate, then it's going to cancel. Yay. So 224 divided by 28 is 8. Is that right? 8/3? 8/3. And 196 divided by 28 should go in 7 times, so 7/3.
I just have a quick question.
Please.
Since you have your calculator out, may you show me how to calculate m of y and equaling to 224 over 3?
Sure. Sure.
Thank you.
Yeah, because this is, you know, it's just stuff that you know, I think on the last test I said there's a problem where I'm like, you know what, just finish it up with numerical integration. And numerical integration, just in case you're not clear on this, that means FN int. That's your numerical integration. So you get to that by pressing math 9 on a TI 84 or 83. The commands on the 83 are going to be a little bit different, but they'll still do it. So math 9, 0 to 8. How about if I do 0, then up arrow to 8, 56 x minus 7x squared dx. Now keep in mind, when we calculate m sub y, there's also this 1/8 out in front, so we're gonna have to divide that by 8. You know what, let's just do it all in one go. It gives me this ugly expression, but if I hit the math key and then press enter twice, it turns it into a nice, neat fraction. So, good question. How are we looking on that one? Does that help out? Is that what you're looking for, Marissa?
Better now. Thank you so much.
Mm-hmm. And you can do likewise for MX. You know, there's not going to be that many problems where I want you to do all the grunge work of evaluating the integral of a polynomial. Where I want you to do it out by hand, I'll ask. I'll say, hey, you know, show me your work here. But if I say use FN int is what helps out you and me, because I don't want you getting this problem wrong because you made an arithmetic error, all right? You made an error, I want it to be getting here, all right? But I don't want you getting the points taken off by simple arithmetic mistakes. We're beyond that. All right, looks good. Looks good. Let's see if we can't do one more and then take a break. Any comments on this one before I move on to another example?
How come you square the outside of mx, but you square the inside of my?
I didn't really square it. If you take a look here, what I had was, and let me see if I can't put it in a, here, I'll use this very manly orange. There we go. If you look here, I had 56 minus 7x times 56 minus 7x. I had that twice. So multiply by itself, that's why I got the squared. Here, I didn't square the insides, I just distributed the x. So it was x times 56 and x times minus 7x. So it just came about by simplifying the integrand, really.
Thank you for the clarification.
Sure. Appreciate
Yeah.
your questions as always.
On top, you did the 1/8 times 1/8 times 1/2. That's how you got the
Yes.
128, right?
Yeah. So 64 times 2 is 128. So I took all that out, and then the only things left was this times this, which is the square. So even better.
One more thing, it looks like your battery is low, so connect your charger.
Oh, on my calculator?
No, your computer.
Oh. Oh, yeah. That's odd.
I thought it was mine for a second. That's why I was like, what's going on?
Uh-oh. That's odd. Oh, there we go. So, I'm not sure I'm going to go bother editing that little quick commercial for HP. I find it so annoying. Every time I use an adapter that's not the one that came with this, they're like, oh, why don't you get an HP adapter? I'm like, yeah, well, why don't you put the price a little bit more reasonable? All right. All right, good one, good one. Let's take a look back though, real quick at our drawings. So our final center of math was 8/3 in the x direction and 7/3 in the y direction, so 2 1/3 and 2 2/3. So that looks pretty reasonable. Yay, good for us. And yeah, good on you for noticing that. They played a little game with the X and Y coordinates there. I didn't quite notice that. So thank you. Let's move on. So here's our center of mass problem in this particular example. So our function is y equals 3 over x, y equals 0, x equals 1, and x equals 2. So we've got 4 different functions that are bounding your region. And kind of like the last one, we're to actually guess which one of these represents the center of mass. So let's start by looking at x equal 1 and x equal 2. What are those graphs going to look like? Anyone? Are they going to be vertical or horizontal lines?
It's going to be either the first one or the fourth one, because x equals 1 and then x equals 2. So I guess it's
Yeah.
Is it horizontal? I'm sorry. I was like,
Yeah, no, these are vertical. Yeah.
Oh, vertical. I'm sorry. Vertical.
Yeah. No, you're right. But you're spot on though. I mean, these two have to be it because these two are horizontal lines. That would be y equals 1 and y equals 2. So you can throw out these two right away. Has to be one of these. And
4 looks better.
yeah, 4 looks better. I mean, this looks too heavily weighted to the left to be the right one. I mean, it's tough to say without actually doing the calculations. I mean, maybe, you know, maybe it is this one, but I put my money here. It's a little bit tighter. Say again? All right. So let me draw this and we'll get going on this calculation. So yeah, as far as your pictures are concerned, you might want to copy this one down. I'll be doing likewise on mine.
Can you scroll like an inch up for half a second?
Yeah. Just a second here.
There you go.
There you go.
Thank you.
Uh-huh.
I'm good. Thank you.
Mm-hmm. Okay, so let me switch over to my rendering right here. So we've got x equal 1, x equal 2, y equals 0, of course, is the x-axis. I'm not going to draw that in. And this is our function y equals 1 over, excuse me, 3 over x. We saw in the last example that the mass kind of factored out. So, I mean, yeah, the density factored out. I'm not going to bother to put that in my future calculations. I'm just going to calculate m equals 1 to 2 of 3 over x dx. This is essentially calculating the area, which we're going to use as a stand-in for the mass. That's going to be 3 times the natural log of x between 1 and 2. I don't really need the absolute values because these values are already positive. So it's going to be 3 ln of 2 minus 3 ln of 1. And the nice thing for us is that that's 0. So the mass overall is just 3 ln of 2. Cool. Now there's a couple other things we need to find. The first of which would be m sub x or m sub y. So let's start with m sub y. That's going to be the tendency to want to rotate around the y-axis. So that's going to be an integral from 1 to 2. And I need two things. I need the distance to the y-axis. So how far that center point is in the y-axis. And then times the area. The area is going to be the force that it rotates around the y-axis. What's that distance here?
X.
Just x. And that's kind of nice about your m sub y calculations. It's just x. So x times the area of that slice. And the area of that slice is going to be pretty straightforward. It's going to be the height times the thickness. So it's going to be 3 over x times dx. So area of one slice. Something interesting happens here. Does anyone see what it is?
3.
Is he at 3?
Yeah, it's just 3, right? And that's really just the area underneath the curve of 3 between 1 and 2. So, I mean, you can calculate it out with an antiderivative, but it's just going to be 3. Let's try m sub x. M sub x is going to be a little bit more involved. So again, it's going to be an integral from 1 to 2. But there's two things I need now. I need the height. So
I'm
the
sorry.
height,
How did you get 3?
well, if you think about what that represents, 1 to 2. It's the area underneath this curve, y equals 3, between 1 and 2. So it's just the width times the height. 2 minus 1, the width is 1, times the height, just 3. You could also find an antiderivative. You could do 3x between 1 and 2, which gives you 3 times 2 minus 3 times 1. And that would also give you 3. So either one on that one would work. Let's find m sub x here. M sub x is going to be the tendency to want to rotate around the x-axis. It's as if the x-axis was a door hinge and you want to know how much force that plate is turning with, so that that force is going to be felt right at the midpoint or the middle of this height. So we're going to have to find the average height. So it's going to be 1/2. I'll tell you what, I'll put it this way, top plus bottom times the area of one slice. So that's what you're going to do. And let's see if we can't fill in some things here that make sense. The top function is just 3 over x. The bottom function is 0. Area of one slice is going to be the height times the width. What should I use for the height?
dx. I mean,
3 over x.
All right, 3 over x to the height, and then dx for the width. Okay. So if we clean that up, that's the integral from 1 to 2 of 3 times 3 is 9 over 2x squared dx. Do you want me to find the antiderivative here or skip the happy ending?
Just
Happy
skip.
ending,
Yeah.
happy ending works. That's going to be 9/4. Of course, the antiderivative of that's going to be negative 1 over x times 9/2, etc. But 9/4, sure. So let's finish up our calculation. You get x bar and y bar, or m sub y over m, and m sub x over m. Let's see. M sub y, where was that? That was 3, right? So it's going to be 3 over ln of 2. Oh, it was 3 ln of 2, wasn't it? Where is it? Yeah, 3 ln of 2. And then m sub x, which is going to be 9/4 over 3 ln of 2. The 3's in both of these cancel out, so you're left with 1 over ln of 2. 3 cancels there. The 4 I can bring down into the denominator. So it's going to be 3 over 4 ln of 2. Hey, probably want to get some numerical values if you're going to check these and make sure that your answer at least looks reasonable. So this is approximately 1.44. This is about 1.08. Let's see how that compares to our graph and see if it makes sense. All right, so the 1.44 seems to work pretty good, and something a little bit more than 1, that works as well. Let's just compare it over here. No, neither of those work, right? This is less than 1 on the y-axis, it's less than 1.44 on the x-axis, so definitely the bottom right one is the correct answer. And it looks reasonable, looks better. That was what our intuition said initially anyways. Okay, let's take a break here.